Okay, so now in this video, now that we have a little handle on how to affect the shape of our cells, let's talk a little bit about composition. So this is Orchard's supposed to be a sort of categorical proof of system. I mean, the main thing you can do in any category is compose things, but since it's higher categorical, those compositions are supposed to only be defined up to coherent cells and things like that. So what I hope we can work towards by the end of this is we'll try and prove associativity of composition. Okay, so we'll start out with a blank editor window here, and we'll just start putting in some cells. And so I haven't said the main way to do that, but the main thing you do is if you have a blank cell, by blank I mean one of these white cells that we were sort of creating in the last video. So you've made a shape where you have a bunch of blank cells, and you want to assume that a cell exists there. Then you use this command, assume variable. So I've selected this open box right here, and I'm going to assume there's a variable in there, and I'm just going to call it x. So basically, and this is the first time we've introduced a new assumption into Orchard, but it remembers what x is. X is an assumed object, and so again, assumed cells appear in yellow. Okay, so so now I'm going to change the shape a little bit. We're headed towards composition, so we're going to need at least two other objects. So I'm going to give myself two other objects, and Orchard has highlighted some of these cells green instead of white, but they're still empty because they have no label, and I'll explain what the green means a little bit later on. But for now, we're just gonna put a new object here. We want a second object called y, so I'll assume a variable, and so I can do that by selecting the cell and choosing assume variable from the menu, or Control A is the keyboard shortcut. So if I press Control A, I can assume a variable, and I'll call it y. Okay, so far so good. Now, one thing that's not apparent in dimension 0, but it becomes apparent in dimension 1, is if I click here, I can't, you'll notice this cell highlights y, and this blank empty cell right here. So I can't assume a variable yet. And the reason is because it doesn't make sense to assume a variable, say g right here, an arrow from y to something, when I don't know what that something is. So Orchard will only let me assume a variable if all of the faces of the box that I'm trying to assume are filled in. So I can't assume something here. I need to put a cell here first. So I'll select this and assume a variable called z. And now Orchard will let me assume a variable here because all of its faces are filled in. Okay, so let's just assume, so the same goes for this box right here. All of its faces are filled in, it's x and y, so I can Control A and get a new variable. And then I can Control A here and get a new variable. Okay, so now what have we done so far? We've assumed that we have three objects, x, y, and z, and an arrow f and an arrow g. So this, of course, to any category theorist immediately thinks, well, okay, what about the composite of f and g? And Orchard will let me form the composite of f and g. So to do that, what I'm going to do is I'm going to use this extrusion. I'm going to select both f and g, and I'm going to extrude. Okay, and when I do that, I get two new cells, just like I always would, except for they're green. And so now I'm going to tell you what the green means. The green means those cells can be filled in axiomatically. So the green is sort of recording the only inference rule, if you like, of this logic, which is that when you see green cells, you can fill them in. And they're filled in not as assumptions, but as consequences. So they're always going to come in pairs, and you fill the top one. So here I got this one and this one. I'll select the top one, and I will do this command up here, which is fill nook. Okay, so if I select that, Orchard will now ask me for a name for both the composite and its filler. I say composite, but it won't always be a composite. But in any case, I'm going to name in this case it will act as the deposit. I'm going to call it GF, and I'm going to call the filler def GF. And when I do that, Orchard fills this in, and suddenly we have this new cell, which is not an assumption. Again, it's a consequence. And filling these holes is, as I said, the only inference rule of our logic. And so GF became the sort of target here, and Orchard knows that this top cell has to be universal. That's one of the it's the rule for filling, essentially. Okay, so we have our first example of a composite. So we had two composable arrows, and we formed their composite, which was also a one cell, and we got a two cell, one dimension higher, recording that definition. Now, if you know much about higher category theory, you know that composites shouldn't be unique in any sense. They should be defined by a universal property. So Orchard also implements that idea, and it implements it as follows. So let me get a new sheet where we're going to form another composite, and we're going to see that it's in a sense equivalent to the one we just made. So to get a new sheet, there's a couple options. Well, first I can just choose new sheet here, and then I'll need to build enough shape to add the cells that I want using the extrusion techniques. Or if I know that I want to start from a particular shape, I can either choose it in the environment or choose it in the builder and double click on it. So I'll double click. I want to start with F in my new sheet, so I'll double click on it in the environment, and Orchard gives me a new sheet to play with, and it's started F already in there. So now I just want to get back to this position we were with G as well, so I'll extrude around Y and give myself some open space. And then right here, I have this cell G, which goes from Y to Z, so I know it can be pasted right there. So to paste a cell into empty space, what I do is I select it in the environment, and I use this command, use cell from environment. So if I do that, Orchard will check that it fits, and if it fits, it will go ahead and move it over here into my workspace. So now I could notice we're exactly in the situation we were when we defined the composite of GF. Let's do that again. Let's first extrude. Notice that Orchard is telling me this is green, as in go ahead and fill this cell in. So I select the top cell, and I'll use fill nook, which is my way of accepting Orchard's offer to fill that cell for me. And this time I'm going to call it GF prime and def GF prime. Okay. So, right. By the way, if I had put in GF and def GF, if I just repeated what I had done for the first definition, Orchard will complain. It will never allow me to have two cells that are named the same thing. And this is sort of a way of enforcing this idea that, if you like, liftings are not unique, and my only inference rule is a certain lifting property. It's not so important for right now. But in any case, what might strike you is that I now have G composed with F, and I've defined it in two ways. I went back and made a first definition, and then I made another cell, which is a definition, and Orchard is sort of remembering that that I can have more than one cell which act as a composite for F and G. Now, what would you expect about those two cells? Well, we would expect that those two cells should be isomorphic because they're both composites of F and G, and we can in fact show that. So let me do the following. Let me open GF in a new window here. So I'll do that by double clicking on it, and Orchard will give me GF. Now I'm going to extrude around it, and then I'm going to take my GF here, and I'm going to select this cell right here, and I'll notice that GF prime fits in that cell right there. So I'll pull it out of the environment and stick it in my pasting diagram. And so here I have GF and GF prime, my two different definitions of a composite for F and G, and I have this empty space filling them. So what I want to say now is that if you stare at this empty space, I can think of it as like a goal. Our goal is to say, well, GF and GF prime are both composites of F and G, we should be able to fill this cell. And moreover, we expect, since they're composites of the same thing, they have the same universal property, we should be able to fill this cell with a universal cell, so one of these blue things. So these blue cells are the only instance of something like equality in this system. To say two things are equal, to say two cells are equal or isomorphic or whatever you like, the only reasonable statement to be made is that there's a cell of one dimension higher, which is blue, which says that those two things are isomorphic. So we're going to try and produce a blue cell between GF and GF prime. And this turns out to not be so hard. Let me go back to here's our definition of FG. And here's how it's going to work. I'm going to stick in, I'm going to extrude around GF here and give myself some space. And I'm going to put GF prime right here. There it is. It fits in that cell, so I can use from the environment. I can stick it in there. Now I'm going to extrude around this cell. And so if I select this, Orchard is telling me that this is supposed to be a two-cell connecting GF and GF prime. And you might notice that we already have one of those. It was the witness for the universal property of GF prime. So this cell fits in that box right there, so I can again use it from the environment by going up here. And by the way, there's the shortcut for use a cell from the environment is Control U. So I'll just press Control U and I'll stick it in there. And then Orchard is telling me, you notice this box and this box turned green. So Orchard is offering to fill those for me. It's saying, okay, you've arranged a diagram where I know there should be a filler for this cell. And maybe in a later video I'll explain what the filling condition is in more detail. But for now, you can just Orchard will find them for you. You can just sort of take your mission in this proof assistant is to find the green cells. So let's click on the top dimensional green cell there, and let's fill it. And the shortcut for filling is Control F. And it will the first box here is supposed to be that cell, and the second box, the filler, is supposed to be the top cell. So I'm going to call this cell iso GF prime, and I'm going to call the filler def iso GF prime. I have this convention where I usually call the fillers def something because they are really recording definitions. Okay, so I'll hit enter there, and Orchard says okay, and it gives me the cell. And if you look at this cell right here, and we can find it, Orchard automatically adds it to the environment. If you look at its shape, you'll notice it's exactly what we wanted. It's exactly a blue cell, an isomorphism from GF to GF prime. And it's a consequence of this lifting property, which is, for the moment, the only inference rule in this sort of diagrammatic logic is I can fill cells, I can fill empty spaces which have a certain property. And again, I'll explain that property more carefully in another video. Okay, so let's start over. And so this is our first example of using universal properties, and it also explains how composite cells are not unique, but their higher dimensional witnesses make them unique up to a higher cell. Okay, so I'm going to press Control N here and get a new editor window, and let's use universal properties to do the associative law. So what's the associative law going to look like? I'm going to build some shape for the associative law, and then I'm going to start assuming some variables. So this first variable I'm going to call x, the next variable I'm going to call y, the next variable I'm going to call z, and the last variable I'm going to call w. Okay, so I'm assuming some objects. Now I'm going to assume some arrows. So let's assume an F, let's assume a G, and let's assume an H. Okay, so here's my setup. Here's a list of cells I've just assumed to exist, and there are three composable arrows. I have F, G, and H. And what I would like to demonstrate is the associativity of composition. Again, always up to a coherent cell of the next dimension. So to do that, we should define the compositions first. So what I'm going to do first is compose G and F, and you'll notice after a while that that making composites always consists of the following two steps. You surround the cells you want to compose with a box, and then you fill, when that box is green, you fill that with the cells that you wanted. So again, repeating what we did in the last one, that's going to be GF and DEF-GF. Okay, but since this occurs so often, there's a shortcut for exactly that setup. So for example, I want to now compose H with GF, so I'll select them, and instead of doing it in two steps, extruding and then filling, I can press Control-C, or go up here and choose Compose Selection. Control-C is the shortcut, and Orchard will do both the steps at the same time. It will extrude for me and then fill. So this I'm going to call HGF and DEF-HGF, with the parentheses one way. And you see Orchard just did the extrusion and the filling at the same time. So when you're composing things, it's very convenient not to have to do it in two steps, but just do it in one. Okay? Great, so now we have GF, which goes from X to Z, and we have our one direction associative composite, which goes like this. Let's go ahead and make the other one. So to compose the other way, we're going to want to start with our F, G, and H again in an empty thing. And as I've said, you can start a new sheet with a cell already embedded in it by just double-clicking in the environment. Then let's give ourselves some space. Let's fill this with G. And let's fill this with H. Okay, so in the first sheet, what did we do? We composed G and F first, and then we composed the composite over there. In this sheet, we're going to do the reverse. We're going to compose H and G first. So I'll hit Control-C. Again, since this is a simple composition, I'm going to skip the extrude and then fill and just do it all at once by hitting Control-C. I'll call it HG and DEF-HG. And then I want to compose HG with F, so I select HG and I select F and Control-C. And this will now be called HGF with the parentheses the other way. HGF. And I get the composite the other way. So you can see the difference. The first one we composed up top and then composed with the bottom, and the second one we composed in the bottom and then composed with F. Okay, and so we now have these two cells. Let me open the first cell we did was here. I'm going to double click and get a new sheet. There's HGF. It goes from X to W. It's the composite of those two arrows. If I extrude around it, I notice that the other direction composite, HG first and then F, also fits in there. And the associative law, if it exists, should be a higher coherence cell, which is, again, blue, because we expect the associator to be an isomorphism. So we would like to find a blue cell filling this empty cell right here. So how can we do that? What I'm going to do is I'm going to use some universal properties. So the first thing I'm going to do is I'm going to go back to our original sheet 1 here, where we compose first this way and then this way. And then what I get is I get two universal cells here. And it turns out to be a consequence of Orchard's inference rule that if I compose two universal cells, the result is also universal. So here we're going to do a composition in dimension 2. I have these two cells. I'm going to hit Control-C to compose them. And I'm going to call it univ, and I'm going to call it HGF. And I'll explain why I'm calling it this in a second. And again, and I always get two cells when I compose. And right, so the composite of these two cells is a 2-cell behind them. And I get, as always, a witness in the next higher dimension. Okay. The reason I've called it univ HGF is, you see, anytime I have a universal cell, it's expressing the fact that that its target, which here is HGF, is universal for all of its sources. So its sources, using what I've showed you about how Orchard highlights the lines. So look at that line right there. That's F, that's G, and that's H, and those are exactly the sources of univ HGF. Actually, if I select it down here, it will probably be easier to see. The sources are F, G, and H, and the target is this thing. So this cell, this derived universal cell, is expressing that HGF, with this composition order, is universal for this triple pasting diagram. Now, if we go to the second sheet, where we've composed in the other direction, and do the same thing, I'm going to select those two cells and compose them. I'm going to call this one univ HG F with the, again, parentheses the other way, and its definition. And if I look down what Orchard has done at this cell I just got, it expresses the fact that HG composed with F, HG composed and then composed with F is also universal for the same pasting diagram. So why is that good? Well, it says that, remember, universal cells are like witnessing that this cell is a composite of this. So we defined our two associative things in two different ways, first by composing one and first by composing the other. But by composing their universal cells, we're able to show that both of those cells, HG and F, and the other HG and F, sorry, it's hard to say that, both of those cells are universal for this other pasting diagram, the one with just 3 arrows. And when you have two cells which are universal for the same pasting diagram, you can always get a cell in between them. So what I'm going to do is I'm going to open this univ cell here, and now I'm going to extrude around HGF, and I'm going to notice that our other composition, HGF, fits in that green cell right there, so I'll use it from the environment. Now I'm going to go over here and I'm going to extrude around these two, and then I find that this back cell here connects FG and H to HGF composed with, where HG composed first, and that's exactly this cell right here. You notice this cell right here interpolates between those two, so I can use this cell and stick it in there, and sure enough, Orchard has decided that this is a fillable condition. And that's why these cells have changed to green. So if I go select this one and do Control F, I will name this cell Assoc FGH and def Assoc FGH. Okay, and Orchard fills those for me. And if I go look at this in the preview pane, it shows that it's exactly what we wanted. It's exactly a universal cell connecting HG and F to HG and F composed in the other order. Okay, so this is how you can start to use universal properties to derive higher coherence cells inside of Orchard.